This is Vijay Jyotish with a critical, time-sensitive engineering intelligence advisory on NASA's Artemis II, the historic first crewed mission around the Moon, currently scheduled for 8:29 p.m. Eastern Standard Time on March 6, 2026. After exhaustive analysis of the mission timeline, I have identified multiple high-probability technical risk clusters that could affect the vehicle, the countdown, the ascent, and the return. If you are following this historic flight, stay with me. This advisory could be the difference between a smooth mission and another multi-month delay. Let's go straight into the briefing. The most critical event is a stubborn software glitch in the ground telemetry processing pipeline. This pipeline will be unable to handle the massive, real-time data volume generated by the SLS and Orion. More than 27,000 individual telemetry channels, including tank pressures, propellant temperatures, valve states, vibration sensors, electrical bus voltages, avionics health, and video streams, flowing at high data rates. The glitch will manifest as buffer overflows, processing lags, frozen displays, or corrupted data packets. These problems will trigger automated safety interlocks, repeated validation failures, and at least one go, no-go pole reversal. This will bring the launch within 10 to 20 minutes of a full scrub. Ground engineers will isolate the root cause, likely a bottleneck in the data handling software running on Launch Control Center computers. They will deploy a targeted software patch or redundant processing workaround, recycle the countdown clock, and clear the vehicle for liftoff. No loss of vehicle risks are indicated. The mission will achieve all primary objectives. First crewed flight beyond low Earth orbit since Apollo 17. But several phases will require real-time workarounds, post-flight engineering reviews, and possible minor trajectory corrections. Phase 1, propellant loading and conditioning. T13, 45 minutes to T5, the NITS. This phase loads the cryogenic propellants into the core stage, CS, and ICPS tanks, while conditioning all ground and vehicle systems for flight temperatures. It is the longest and most fluid dynamic phase of the countdown. Anomalies will center on LH2-related steps due to its extreme cold and volatility. 1. GLS activates, ground launch sequencer activates. This is the primary automated computer system in the Launch Control Center that orchestrates and monitors every subsequent step in the countdown sequence. It will run normally, but will immediately begin logging early sensor discrepancies that foreshadow later loading issues. 2. 2H45M hold, 2-hour, 45-minute hold. A planned, built-in pause to allow teams to resolve any early issues before committing to propellant loading. This hold is likely to run longer than planned as teams chase minor early sensor or sequencing discrepancies. 3. Go for prop load, go for propellant load. Official launch director approval to begin flowing propellants. Approval may be briefly delayed while engineers confirm initial conditioning data. 4. CS-GSE chill-down, core stage ground support equipment chill-down, cooling the groundside pipes, valves, and manifolds to cryogenic temperatures to prevent thermal shocks during filling. Expect extended chill-down times or uneven cooling caused by temperature sensor fluctuations. 5. CS-LH2 slow fill, core stage liquid hydrogen slow fill. Initial slow rate filling of the core stage liquid hydrogen tank with super cold liquid hydrogen at minus 423 degrees Fahrenheit. High risk of erratic pressure and temperature swings, micro leaks at seals or valves, and false high-low readings from sensors, causing interrupted fill sequences. 6. CS-LOX slow fill, core stage liquid oxygen slow fill. Initial slow rate filling of the core stage liquid oxygen tank with liquid oxygen at minus 297 degrees Fahrenheit. Similar but milder sensor and flow irregularities may appear. 7. CS-LH2 fast fill, Core stage liquid hydrogen fast fill. Transition to higher flow rate once temperatures stabilize. Flow irregularities or valve issues will likely interrupt the fast fill, forcing pauses or manual overrides. 8. CS-LOX fast fill. Core stage liquid oxygen fast fill. Same transition for LOX. Minor flow or sensor anomalies expected. 9. ICPS GSE chill down. Interim cryogenic propulsion stage ground support equipment chill down. Cooling ground systems for the upper stage ICPS tanks. Extended times or uneven cooling similar to core stage. 10. ICPS LH2 fast fill. Interim cryogenic propulsion stage liquid hydrogen fast fill. Filling the ICPS LH2 tank. Same LH2 specific leaks, pressure swings, and false sensor readings. 11. ICPS LOX fast fill. Interim cryogenic propulsion stage liquid oxygen fast fill. Filling the ICPS LOX tank. Milder sensor anomalies. 12. CS LH2/LOX topping. Core stage liquid hydrogen/liquid oxygen topping. Final topping off of core stage tanks to account for boil-off. Multiple extra topping cycles will be needed due to higher than expected boil-off or small leaks. 13. CS/ICPS replenish cycles. Core stage/interim cryogenic propulsion stage replenish cycles. Continuous topping to maintain proper fill levels as propellants boil off. This step will see repeated replenish cycles triggered by ongoing boil-off or leak rates. 14. 70-minute hold. Extended planned pause after loading to verify tank pressures and thermal stability. This hold will almost certainly run longer while teams troubleshoot sensor discrepancies or minor leaks. Phase 2. Holds, go pole, and terminal countdown T0510 to T0004. This phase transitions from propellant loading to final vehicle and crew preparations, with increasing automation and human decision points. This is the peak window for the major software telemetry glitch. 1. 30-minute hold. Final short built-in pause for last system checks. This hold is likely to be extended due to ongoing data validation issues. 2. LD go poll. Launch director go, no-go poll. Formal poll of all engineering and safety teams for final launch readiness. The ground data systems will be overwhelmed by the real-time influx of more than 27,000 telemetry streams, causing buffer overflows, frozen displays, or corrupted validation checks. This will likely produce a no-go from one or more teams and create the highly visible near scrub situation. 3. Terminal count. The final automated and manual countdown sequence where all systems are brought to flight-ready status. Repeated automated holds will occur here because of the same telemetry overload and corrupted data packets. 4. Crew arm retracts. Retraction of the crew access arm that connects the launch tower to the Orion crew module hatch. Mechanical hesitation or slower than normal retraction may appear if upstream sensor data is delayed. 5. CS tank press, core stage tank pressurization. Pressurizing the core stage propellant tanks with helium to flight pressure levels. Sudden pressure spikes or drops are expected due to ongoing fluid anomalies and telemetry lag. 6. Orion internal. Final internal pressurization and conditioning of the Orion crew module cabin and systems. Minor pressure or environmental control fluctuations may occur. 7. LAS armed. Launch abort system armed. Arming the solid rocket-powered abort tower atop Orion, enabling it to pull the crew away in an emergency. False positive or false negative arming indications are likely because of corrupted telemetry data. 8. FTS armed, flight termination system armed. Arming the range safety destruct system that can destroy the vehicle if it veers off course. Similar false arming indications may appear. 9. LH2 bleed, liquid hydrogen bleed. Controlled venting of excess LH2 vapor to maintain proper tank pressures. Irregular bleed flow rates will be seen due to lingering fluid anomalies. 10. CS APU starts, core stage auxiliary power unit starts. Starting the hydraulic power units that drive the core stage engine gimbals and thrust vector control. Electrical transients or slight startup glitches may occur. 11. CS replenish ends. Final cessation of propellant replenishment before committing to launch. This step may be delayed while final fluid stability is confirmed. Phase 3, final pre-ignition sequence, T004 to T plus 0000. This is the final automated sequence leading to engine start and liftoff. 1. Purge sequence 4. Final nitrogen or helium purge of engine ducts and lines to remove any residual moisture or contaminants. Incomplete purge or lingering contaminants may be detected because of earlier fluid anomalies. 2. ICPS internal. Final internal conditioning of the ICPS avionics and propulsion systems. Minor avionics or conditioning glitches may appear. 3. ICPS replenish end. Final stop of upper stage propellant topping. Timing may be slightly off due to carryover from loading issues. 4. Go for ALS, go for automated launch sequencer. Handover from ground sequencer to the vehicle's onboard automated launch sequencer. Potential last-second data validation hiccups may delay this handover. 5. ALS starts. Automated launch sequencer starts. Onboard software takes full control of the final 33 seconds. Minor timing offsets may be seen. 6. Hydrogen burn-off. Ignition of small hydrogen flares at the base of the vehicle to safely burn away any leaked LH2 vapors before main engine start. Incomplete burn-off with lingering vapors is likely, causing sensor trips. 7. Engine ignition. Ignition of the 4 RS-25 core stage engines. Rough or staggered ignition may occur, with one or more engines lighting slightly out of sequence. 8. Liftoff. Vehicle release from the launch pad and initial ascent. Higher than nominal vibration or pressure spikes and brief umbilical disconnect transients are expected. Phase 4, ascent phase, T plus 00000 to T plus 0318. This covers powered flight through the atmosphere until the launch abort system is no longer needed. 1. Tower clear, T plus 0009. Vehicle clears the launch tower. This should be clean, but any prior vibration issues may leave slight residual effects. 2. Max Q, maximum dynamic pressure, T plus 0110 second. Point of peak aerodynamic stress on the vehicle. Higher than expected aerodynamic vibration and structural stress readings will likely require real-time flight computer adjustments. 3. SRB separation, solid rocket booster separation, T plus 0208. Jettison of the 2 5-segment solid rocket boosters. Minor asymmetric timing, small debris generation, or unexpected hot gas impingement on the core stage may occur. 4. LAS jettison, launch abort system jettison, T plus 0318. Safe separation of the abort tower once the vehicle is past the point where abort is feasible. Brief sensor confirmation lag may appear if upstream telemetry problems persist. Phase 5, upper stage and Orion separation phase, T plus 0806 onward. This phase covers the transition to orbital insertion and crew module operations. 1. MECO, main engine cutoff, T plus 0806. Shutdown of the 4 RS-25 core stage engines. Slight timing offset or residual hot gas recirculation may be seen. 2. Stage separation, T plus 0818. Separation of the expended core stage from the ICPS Orion stack. Minor thrust tail-off irregularities or timing offsets are possible. 3. Solar Array Deploy, T+2000. Deployment of the Orion spacecraft's solar arrays for power generation. Partial hesitation, motor current spikes, or latch mechanism anomalies may occur. 4. Perigee raise burn, T+4900. First ICPS engine burn to raise the low point of the orbit. Slight thrust under or over performance may require small burn time or attitude corrections. 5. Apogee raise burn, T+147 minutes and 57 seconds. Second ICPS burn to raise the high point of the orbit. Similar thrust performance deviation requiring adjustment. 6. Orion separation, T+324 minutes and 15 seconds. Final separation of the Orion crew module from the ICPS. Minor electrical bus transients or brief communications handoff glitches may appear during detachment. Recommended pre-launch mitigation actions. 1. Preload enhanced telemetry buffering, redundant processing nodes, and rapid restart scripts in the Launch Control Center. 2. Prepare pre-approved software patch packages for data pipeline overflow scenarios. 3. Station additional engineers at all GoPole, terminal count, and telemetry stations. 4. Perform extra LH2 valve leak checks and sensor calibrations during the 70-minute hold. 5. Define clear abort to scrub criteria while maintaining an engineering override protocol for the identified telemetry issue. Conclusion. The March 6, 2026 launch will feature a high-visibility software telemetry crisis in the final 15 to 20 minutes of the countdown that nearly forces a scrub. Engineers will resolve it under time pressure, enabling on-time liftoff. Subsequent flight phases will encounter several manageable anomalies, requiring real-time workarounds, but the SLS, ICPS, and Orion will deliver the 4-person crew, Reed Wiseman, Victor Glover, Christina Cook, Jeremy Hansen, safely to the planned translunar trajectory. All issues fall within the demonstrated recovery capabilities of the vehicle. NASA, you can absolutely make Artemis II happen in this window, but it will take everything you've got. Exhaustive testing, unbreakable discipline, and wise calls at every turn. If you pull it off under these conditions, it will be legendary. Yet the question remains, is all this stress, pressure, and cost truly necessary when a more favorable window could make the path dramatically easier, safer, and far less expensive? Millions are on the line with every delay or scrub, extended ops, range time, crew quarantine, rework. The Smart Play combines your world-class engineering with precise Muhurta alignment to pick the optimal slot. It's not either or, it's both and for maximum success and savings. NASA teams, I admire what you're building for humanity. This advisory is here to help. Reach out anytime. I'm ready for confidential consultation. Subscribe for real-time updates as we approach March 6. Drop your thoughts in the comments. What concerns you most about this window? This is Vijay Jyotish, Engineering Intelligence for Artemis II. Let's get this mission to the moon and back safely. Stay vigilant.